Hello everybody, Mr. Hinnon here for some Trebuchet physics. So this part of the projectile motion lab, the projectiles launched at an angle, really was playing around with the trebuchet. So I'm going to send you a video of the trebuchet in action. We did a pumpkin chunkin today where we launched a pumpkin during one of the class periods, and we took some video of it. We only really got one good launch, so we'll see how things kind of go. But one of the things I liked about this information, I'd never really used the trebuchet before, was this information kind of here at the bottom of this little document by Donald Ciano. But he mentions that the ultimate angle for maximum range would be 45 degrees, and I thought this was kind of neat, that you want the length of the long arm to actually be 3.75 times longer than the length of this short arm. So 3.75 to 1. We might actually get into talking about that when we get into rotational motion, because if you've ever played around with a seesaw, what you know is we've got heavier weight over here, and we've got a lighter weight over here, but the transfer of that torque, we have torques being equal to each other, actually will affect it. The length of the sling should be equal to the length of the long arm. So in other words, the length of this should be the length as that. So really, when this fully extends, you're not talking about just 3.75, you'd actually be talking about, what would that be, 7.5. So 7.5 times the distance, which is going to be something more important. And then they also mentioned the counterweight should be a mass that's 100 times greater than the mass of your payload. So this should be 100 times greater than the mass of that little object. We're not going to get into all that. We're mostly just trying to figure out what is the velocity of this projectile as it gets launched. So we have a data sheet here that we're filling in. What we did is we collected data for all the classes, and I put it together as the best data. So here is what we've got from first period. We had one of the launches launch it at 76 feet 3 inches. Now when I think about that, I realize this inches has to be converted into feet before I can kind of convert it over. So what I did is I thought of inches and realized there are 12 inches in a foot. So 3/12 of a foot is what we're dealing with here. And so I'm actually going to refer to this as 76.25 feet. What I need you to do is convert that into meters. I need all these in meters. That had a time of 2.64 seconds. Next up, we had a launch of 75 feet, which took 2.41 seconds. We had a launch of 73 feet, which had a launch of 2.71 seconds, which is kind of funny, but that's how it worked. We had something that was 77 feet, 9 inches, which is 0.75 feet. And that one took 2.56 seconds. And then we had 76 feet 3 inches again, and this one was 2.58 seconds. So the idea is I want you to take all this data, convert it into meters, and then you're going to find the average of it. This is going to be our average horizontal displacement, so that's going to be x. We're going to take all these times, because they were all in seconds. We're going to find the average of those. That's going to be my average time. Now, if I were to ask you how to find how fast this thing is going, the initial velocity of this tennis ball that was being launched, most people would go, oh, well, we've got distance and we've got time, or we've got displacement, we've got time. Can I just divide these two, and x over t, doesn't that just give me velocity? Well, that's kind of partially true. It gives you your horizontal velocity, so it tells us how fast horizontally. But now I have to realize that this tennis ball is actually being launched diagonally. So it has an initial velocity that's diagonal like this. What we just found is how fast it's moving horizontally. We found the Vx. I want to know this. I want to know the diagonal velocity. So what I have to add in is the fact that there's an angle to this. And in essence, the tennis ball is doing two things. It's going upward with some kind of VIY, and it's going horizontally. Now, if I take this horizontal or this vertical and put it over here, In other words, I move this over, you actually find that these form a nice little right triangle. And the relationship between VI and VX is cosine. The cosine of this angle would equal my adjacent side, VX, over the hypotenuse, which is VI. This will allow me to find out the initial velocity. Now I want to actually solve it for VI, so when I do that, it would rearrange. VI would actually be Vx divided by the cosine of my angle. For us, we're going to assume that this is launched at a 45-degree angle, just for simplicity's sake, and kind of go from there. So your ultimate goal is first you're going to find x and t to find Vx. Use that to find how fast this Trebuchet launches our little tennis ball. Hope you enjoyed this edition of Trebuchet Physics with Mr. Hinnon at the Institute.